In section 2.1, I will define the quantity acceleration, discuss how to distinguish when an object does and does not accelerate, and show you some examples of how to calculate acceleration. When an object's velocity changes, it accelerates, and the rate at which an object's velocity changes is called acceleration. Galileo Galilei was an Italian physicist who's credited with being the first to mathematically describe the motion of accelerating objects. I'll talk more about how he discovered the mathematical principles of accelerating bodies later in this unit. The definition of acceleration is shown in this equation. Recall that delta means final minus initial, and so we can unpack the delta v in the numerator. Delta v, the change in an object's velocity, is the object's final velocity minus its initial velocity. And I know that the positive physics guy uses s for speed instead of v for velocity, and you can substitute s for speed if you would like, but this does not work if an object's velocity changes direction, if its direction of motion changes. So this is okay to use, but only for motion in one single direction. It's important that you understand that all accelerations are the effect of an unbalanced force acting on an object, and we'll explore this connection in lots of detail in upcoming units. And because a force is a vector quantity, meaning that it has a direction associated with it, for example, say we had an object that was being pushed forwards by an unbalanced force, that acceleration would occur in that direction. The object would accelerate forward. The direction of the unbalanced force determines the direction of the acceleration. The units for acceleration come from its definition. The units for acceleration, and I like to put the little brackets around the symbol for acceleration to indicate that we're just talking about the units of it, are a unit of length divided by a unit of time, because those are the units for velocity and therefore change in velocity, divided by another unit of time. So, for example, say we had an object whose velocity changed by 50 miles per hour. And that change occurred in 10 seconds. Crunching the numbers, 50 over 10 gives us 5. And the units there would be miles per hour per second. So every second, the velocity changes by 5 miles per hour. The rate of change in velocity is 5 miles per hour per second. If the units for the speed or velocity have the same time unit as does the time in the denominator, then we can combine the two time units, say we had time units of seconds and seconds, into seconds squared. Whenever an object's velocity changes, an object accelerates. There are 3 ways for an object's velocity to change, so there are 3 ways for an object to accelerate. An object can accelerate by speeding up, by slowing down, but an object can also accelerate if its speed remains constant. An example of this is a planet that's in orbit around the sun. It orbits in a roughly constant speed, but its velocity is changing because its direction of motion changes. Remember, acceleration is defined as a change in velocity, and therefore a change in the direction of motion would also result in an object accelerating. In the absence of an unbalanced force, so if there is no unbalanced force acting on an object, there will be no acceleration for the object. The acceleration will be 0. And remember that the acceleration is the change in velocity per time. So if the acceleration is 0, that's going to imply that the change in velocity is also 0. So what does it mean for an object to have 0 change in velocity? Well, that will imply that an object will maintain a constant velocity. So for example, if you have an asteroid in outer space, there's no forces in outer space if it's really far away from any gravitational attraction from a planet or a star. If this object was moving with some velocity, it would maintain that constant velocity forever and ever. It would not slow down, it would not speed up, it would not change direction. It would have a constant velocity. Another example is just an object sitting on a table. This object happens to have 0 velocity, and if it has an acceleration of 0, that object will end up being at rest. Physics-wise, an object that is at rest and an object that is moving with a constant velocity are exactly the same situation, because the forces acting on the object total up to 0, or there are no forces acting on it, and so there's 0 force. 0 force implies 0 acceleration. 0 acceleration implies 0 change in acceleration. And an unbalanced force of 0 implies that velocity has to be constant. We use the word decelerate to describe an object whose speed is decreasing. And it's important that you understand that decelerations are just a special case of accelerations. An object will decelerate when its velocity and acceleration have opposite signs, which means that they're in opposite directions. But all decelerations are accelerations, and a decelerating object is changing its velocity. Therefore, a decelerating object is accelerating. Deceleration is just a special kind of acceleration. But it's important that we understand that just because an object has a positive acceleration does not imply that it is decelerating. So if we have an object that had an acceleration in our positive direction, it can still slow down if that object is moving in our negative direction. If the signs of the acceleration and velocity are opposite, this object will slow down. It will decelerate. Okay, so here we have the 4 different combinations, and you can see that an object is always going to slow down when its acceleration and its velocity are in opposite directions. Here we have an object, a car that's moving forward, but it's braking, so it has a negative acceleration. This will slow down. When the acceleration and velocity are in the same direction, then this object is going to speed up. Here we have 2 positive velocity and acceleration vectors, but we can also speed up if we have a negative acceleration. Good example of this is a falling object. A falling object will experience an acceleration that is downwards and therefore negative. And if that object is falling with a negative velocity, well, a object falling down is going to speed up. The opposite of this, an object that is thrown upwards, would have a positive velocity, but if it's in the air, then it's got a negative acceleration due to gravity. This object is going to slow down or decelerate. In this example, we have an airplane landing with a speed of 72 meters per second, and it slows uniformly, or as they might say in positive physics, the speed will change steadily to rest in 12 seconds. We should start this problem by identifying the given information and the information that the problem is asking us to calculate. In this case, it wants us to find the magnitude of the airplane's acceleration and how far the airplane traveled, which is a distance. So I'll highlight all the important information and write it down in a givens table. To calculate the acceleration, we can use our definition of acceleration. And if the airplane is slowing down from 72 to 0, its velocity is decreasing, meaning that we have a negative sign here, decreasing by 72 meters per second. When we crunch the numbers, we end up getting negative 6 meters per second. And that negative sign is indicating the direction of the acceleration. So we had our airplane, and I'm horrible at drawing airplanes. If the airplane was moving forward with some initial velocity, 72 meters per second, in order for it to slow to rest, it would have to have a negative acceleration. Slowing objects have to have an acceleration and a velocity with opposite signs. But the problem didn't ask us to calculate, to comment on the direction of the acceleration. It only wanted to know the magnitude, which was why I put the acceleration symbol in absolute value symbols. The absolute value symbols indicate that we're just interested in the magnitude, which is just the amount. So the negative sign, remember, indicates direction. So we're going to ignore that negative sign, because the negative sign just indicates direction. The magnitude is 6. And when I expressed my answer here, notice that I expressed it with 3 sig figs. And I did that for the reason that all of the information that was given to us, all the numbers, also were given with 3 sig figs. To calculate how far the airplane moved, well, we can go back to our average speed rule, or rather average velocity rule. Velocities and speeds work exactly the same way. And average velocity is distance per time. We can calculate that average velocity or average speed, and we find that it is 36 meters per second. We can rearrange the equation on the bottom for distance. It's average speed times time. Can plug in the numbers, crunch the numbers, and we get the distance is 432 meters. In this example, we have a drag race in which a car accelerates from rest at a rate of 4 meters per second squared to a speed of 32 meters per second. Part A wants to know how long this takes, and Part B wants to know how long it would take the car to reach the speed of 16 meters per second. If I highlight the information, I can then organize it into a table, and you'll notice that I highlighted the relevant information in Part B in a different color. That's to point out that there's a trick that we can use to make a calculation maybe go a little bit faster if we realize that there's a trick to it. So for Part A, we can use the definition of acceleration, rearrange it to solve for time, and notice that I stopped using delta t. Delta t and t are exactly the same, as long as when you start the problem, you're starting at 0 seconds with t equals 0. I can fill in the information that I know. The speed is going to change by 32 meters per second. 0 to 32 is a change of 32. And the acceleration rate is given as 4 meters per second squared. And so this works out to 8 seconds. I know it's probably easy to understand that 32 over 4 is 8, but how did the units turn from meters per second divided by meters per second squared into seconds? Well, remember that when you divide by a fraction, that is equivalent to multiplying by the reciprocal of that fraction. So dividing by meters per second squared is the same as multiplying by seconds squared per meter. Meters are going to cancel out. This leaves me with seconds squared over seconds, which is seconds. So the units end up being seconds. You don't always have to go through this kind of work to figure out the units for your final answer. It can be helpful. It's a nice little check to make sure that you did all your algebra right. If the units worked out correctly to the units that you would want, then there's a good chance that you did the problem right. But what I like to do is just always make sure I'm putting in the standard units, meters per second squared. And if standard units come in, standard units always come out. So we're going to get out standard units of seconds. Now, for part B, it wants to know how long it takes. Well, if we look at the equation for acceleration, you notice that here we have a ratio equaling a constant number. And whenever you have a ratio equaling a constant number, that's a signal that the numerator is directly proportional to the denominator. So the change in velocity is proportional to the time that the car has been accelerating for. So hopefully we notice that the final speed here is 32. This wants us to know how long it takes us to get to 16. Well, 16 meters per second is half of 32 meters per second. So it should take half the time to gain half the speed. Well, I can do that math in my head. It took 8 seconds to get to 32, so it should take half of 8 seconds or 4 seconds to get to 16 meters per second.